Good morning, class. Today we are beginning chapter 4, and the very first problem involves building a mathematical model, using something we'll call bivariate data, and I'll explain what that is in a moment, to make predictions. The title of this first lesson is How Can I Make Predictions? And we're going to be finding something called the line of best fit. Now, admittedly, the problem is a bit contrived. This is fairly artificial. However, collecting data and building a model based on that data and using that model to make predictions is a fairly routine process. So in this hypothetical, Robbie is planning to attend a place called Tinker Toy Tech this fall. And he's visiting the campus with mom and dad, and he will be there through the day, and he knows there's a football game there tonight. Unfortunately, there's no seats. There's no seats to be had. And you could say there's no seats because they're not allowing crowds in. The players have been quarantined, and only people that have been quarantined can go into the stadium. Or you could just say there's no seats, it's sold out, and he can't buy a ticket. But he notices, quite absurdly, admittedly, while walking around the stadium, that there is a hole, and I would not do this because I would be freaked out by spiders, but he peers through this hole, and basically it's lined with a PVC tube, and he sees into the football field. Looking through this hole, he can see a part of the field. And the question that Robbie has is, if he was there during the game, if he was there at game time, how much of the football field could he actually observe? Now, in the problem, he's not able to see the football field at all right now because there's some audio-visual people that have got their trucks parked in front of this hole, and he's not able to see it. He just sees their trucks. So that's why we're suspending belief in, well, why don't you just look through the hole and see how much of it you can see? No, that's not happening. He's going to have to build a model to predict how much of the football field rather, he can see.
So I think we've all experienced this to one degree or another. The further you are away from something, the more of it you can see. And the closer and closer you get, your field of view is diminished. In fact, if you get all the way right up to here, you're just barely seeing like a couple of inches. So in this problem, my students have collected data using this tube, which is reportedly the same length, the same diameter as the tube that Robbie will be watching the football game through. And you can see if I take this tube and put it right over the camera here, right, if I'm right at the wall, I can barely just see 1 inch in my field of view. But as I go back further and further, I can observe two numbers. One of the numbers is how far away from the wall I am, and the other number is what's my field of view. And I can continue to go back further, and again I see how far from the wall I am and what's my field of view. How far I am from the wall and what's my field of view. So using this set of data, right, we can construct a model that will allow us to predict if something is so far away, right, how much of that can I see? And we use this model to predict how much of the football field Robbie will be able to observe through the tube.
So our task today is to use a set of data that was collected by students to build a model to predict what part of this football field we're going to be able to see. The data that was collected was bivariate. That means that you're going to have two sets of number. One is how far away you were or how far away the front of the view tube was from the wall, and the other number is what the field of view was at that distance. Using that, we're going to very carefully plot those points in a scatter plot to help us build a model. Once the data is on the scatter plot, we're going to figure out what a reasonable line that describes that data is, and then we're going to use that line, we're going to use that model, the y equals mx plus b, to make predictions about how much of the football field we can see. So I know when I'm right at the front of the tube, all that I can see is the width of the tube, and I think the diameter of the tube is 1 inch. So at the beginning, we can just see 1 inch of the field of view. But as things go further away, at 50 yards, the question would be, how much can we see? Now the interesting thing is, because our data is recorded, it's inches and inches. So for example, if you're 5 inches away, you can see 7 inches. Those units become immaterial, and we don't have to worry about converting yards to inches. So don't worry about that. The model itself will be unit free, because the units of distance for the field of view, the distance from the wall and the distance of the field of view are both in inches, so that becomes unimportant. That seems kind of counterintuitive, but you're going to have to trust me on this one. Or not. I would love to hear why I'm wrong. So at 50 yards, right, when we plug 50 yards into our model, it's going to tell us how much of the football field we can see there. And then further away, that's 50 plus 100 plus 10 yards, which would be 160 yards away. Right? How much of what width of the field can we see at that point? Now, using those two numbers, right, using those two numbers, we're going to be able to figure out what proportion or what the area of the football field we can see. So if we can figure out the area of that trapezoid, right, that would be a good point to stop. But also you could tell me what percentage of the actual football field you can see as well. And the percentage of the football field that's viewable would be the area of the trapezoid divided by the area of the entire football field. On the Google slide deck today, you're going to need to plot the data set that I'm providing you with. It will not be this large. It will not have anywhere near this many points. If you would like, you could definitely use Desmos or GeoGebra to plot the data, and then just copy and paste that completed graph for you. Once we've got our data plotted, we need to determine what we think is a reasonable line of fit. This line, although the slope isn't bad, it's clearly way below all the data. So this would not be a good model. This has the benefit of hitting some of the data points, but when I squint and look at it, it's clear that the slope of my data set is steeper than the slope of this line. This is better. This is better still. And I really like this. So once we've decided a line that we think fits the data well, we need to determine the equation of that line. And that sounds like a pretty difficult task, except what we really need to do is just find a couple of data points that the line is passing through. And if we can't find those, just find a couple of reasonable numbers that appears that the data is passing through. So for example, this line that I currently have, it looks like 140. It looks like 140 inches has a field of view of 14 inches. So if I'm 140 inches away, it looks like I can see 14 inches from left to right. And on this data set, it also looks like, trying to find another number that's close. Actually, just past that, it looks like 160 is very close to 16 inches. So you just need to identify two XY points that you're pretty confident you can estimate are on the line, and then use those 2 points to come up with the equation of the line described. And once you have that model, that y equals mx plus b, that model that if you give it a distance, it will give you back in the same units the distance that you put in. So if you put in that something is 50 yards away, it'll tell you what the field of view is in yards at that distance away. If you put in something is 160 yards away, it'll tell you what the field of view is all the way at the far end of the football field. And with those two numbers, the length of those two bases of that trapezoid, we should be able to figure out the area of the football field we can see, and then we can answer the question what portion of the football field we can see.